Can I ask a question?
Go ahead, Ori.
Hi, Alice.
Oh, hi, Ari.
How's it
Long
going?
time.
Yeah,
Good, you?
yeah, good. I actually have to go teach in a few minutes, so I'm happy I got the chance to ask the first question. Um, I'm just wondering about these quasi-static approximations especially those that you talked about in the first part of your
Yes.
talk. Um, So if I understand correctly, you're looking at a limit where the size parameter, I think you called it uh,
Delta. Yeah.
delta, goes to zero. I'm just wondering what happens in your examples with the damping factor big gamma.
Uh,
So you have the loss parameter in the Drude model.
yeah.
Um, is that presumably that's a parameter that you consider to be fixed in your analysis?
The omega p or the t? Yeah.
No,
In the right.
the big
T. Sorry.
T. Oh yeah, it's a T. It's not a gamma. Sorry.
Yes.
Yeah, yeah. So I just maybe a warning is that if if um if this T is I guess large in your case, you have a 1 over T there.
Yeah.
Um, so if the loss is very small, then you have a stronger and stronger resonance potentially,
Mm-hmm.
and the particle will scatter increasingly stronger, increasingly strongly. Um, and what could happen is that your quasi-static approximation would no longer be valid. So the classical quasi-static approximation is delta going to zero, but you need to be careful in these situations with resonance. If the loss is too small, then actually the condition that delta needs to satisfy becomes more and more strict. So delta needs to become
Yeah.
smaller and smaller.
Mm-hmm.
And in fact, you can think about like distinguished limits where delta is small and T is large, and you get a regime which is not the classical quasi-static approximation,
Mm-hmm.
but it's sort of quasi-static in the sense that the near field is electrostatic, but the radiation damping is important at leading order, so the radiation to infinity. So I'm
Okay.
just wondering if um, and that regime is very common actually when you run numerical experiments and actual measurements, because um, if you compare numerical experiments um, to quasi-static approximations, then sometimes you're very much surprised by how bad it works, in the sense that your particle needs to be really, really small compared to the wavelength for it to work. And the reason is that there's this distinguished limit where close to resonance, your particle is scattering so strong that the radiation damping is in fact important,
Mm-hmm.
even though the particle is extremely small compared to the wavelength. So I'm just
Yeah.
wondering if that's something you've considered, or is that a regime in which you could generalize your analysis to?
So it's not something we've considered theoretically, but it's something we have observed numerically, especially in the second part when we added the emitter close to the nanoparticle and yeah, the
Okay.
size.
There's a simple physics correction that you can find in the literature.
Okay.
So you just sort of calculate the radiation damping associated with the electrostatic dipole, and then you can correct the quality factor to account for that. But that's not really a complete correction, because it doesn't correct for the for example, it doesn't correct the frequency shift properly. So yeah, it would be interesting if these methods could be extended not just to the beyond the classical quasi-static limit, but in a distinguished limit where delta is going to 0 and t is going to infinity in some appropriate way connected to how small delta is.
Yeah. Thank you.
Great, thank you. I mean, I had a related, if somewhat more naive question, which is, I mean, presumably your theoretical results are pretty specific to this Drude model, right? My question being, can you, if I decide I want to use a different model for the permittivity, well, I mean, is that a minor alteration of your theory, or is that more fundamental?
No, it's quite minor, because we only use it for explicit calculations of the plasmonic resonances, and we don't really need these resonances in the theory. So as long as it incorporates the right physics, which is losses and negative imaginary part, I think it would be quite a small change. We've played around with different permittivities, actually.
And you get similar agreement with your numerics? All right, cool. Would anybody else like to jump in with a question? I will press on with some questions if nobody speaks up.
Okay, let me jump in.
Go on, so.
Yeah. Okay, so here you assume some Drude model, but of course you have many other, types of models, Drude Lorentz, etc., etc. So it would be some minor change or radically new theory if you would change this epsilon of omega. If you have a different kind of dispersion with more poles, with
I think
so the dispersion of your particle is very specific, but you have many models for the dispersion of the particle. So how would you implement a different dispersion?
So I don't think it would change massively the results, as long as we have something with negative, so that models the same physics. So radiation losses, absorption, and we have a negative imaginary part. It would change slightly the resonances, but I think it would be very minor because we checked our resonances against the physics literature and it's very close. So I think the Drude model is actually quite a powerful model in the range that we look for, yeah.
In the same spirit, now perhaps another minor change. Could you allow some anisotropy? So could epsilon be matrix valued? At least it makes sense if epsilon is a 2x2 matrix, because it's a transverse case.
This I haven't looked into.
Because you could play lots of nice games. You can have a different dispersion, in the two eigenvalues. I mean, you could end up with very strong anisotropy. I mean, so you would have an effect of directivity. I mean, something quite cute.
Okay. Yeah, we haven't looked at that at all.
And also, so this is Helmholtz so far, or you've got some curl operator?
So we've done. We have some results for the Maxwells as well.
And so how do you handle the how do you handle the Maxwell case?
So from Maxwell's, we start from the Lippmann-Schwinger equation.
Okay.
And instead of the Neumann-Poincaré operator, we end up with this magnetization integral operator. So it's a volume integral instead of being a boundary integral, which has some advantages.
But I guess that you would prefer to work with the magnetic field as the unknown because it's divergence free, and unlike the
yeah.
I mean,
Well, we've done in the paper about this, we've done the electric field.
you've done the electric, okay.
Mm.
But so when you write it for the electric field, your 1/epsilon, it is outside the curl. You know, it's not
Yeah.
curl 1/epsilon curl. It's your epsilon is not sitting inside the curl if you do it in the electric field polarization.
Yes. So I don't have any slides on this.
Yeah, you
but,
would just have it's just out of curiosity. Okay. So no. Okay. So you do it. Yeah, you do it with the Maxwell system rather than doing it with the second order. Okay. So you work both in E and H. Okay. Wow. But it's always isotropic. You don't have any
Yes.
anisotropic.
No. Once again, here it's all isotropic.
Okay. Great work anyway. So I will stop there. Thank you so much.
Thank you.
Thanks, Seb. And then, I mean, another related question, Alice. If you made your particle non-dispersive, I mean, arguably a less interesting case, but I mean, you commented that the high, you no longer get or you implied that you no longer get this nice behavior whereby the high frequency approximation still works.
I think it would just not scatter light if it's very small and doesn't have a resonance. I don't think. And do you have something else in mind, or just a small, transparent?
No, yeah, exactly. Just something very small with I don't know, maybe very highly contrasting, but constant material parameter.
So we haven't looked at that yet. We plan to look at the electric case, high contrast, but we haven't yet. I think it's quite challenging for other reasons.
Yeah, no, it's different. Okay, I had another question, which was, I mean, with this integral theory, it should handle it nicely, but how would you modify this from like multiple particles? So a system of multiple nanoparticles.
I don't think it. Yeah, I mean, unless they are very close together.
Yeah.
Which would make it a lot more complicated. When we have close to touching particles, it's always
yeah, it's a whole nother ball game.
Yeah, a whole I guess what Sang-Jung's been working on.
Yeah, exactly.
Yeah. But if they are not close together, I think the framework could be quite easily adapted.
Yeah, I guess your integral operator can, like, is there anything stopping you from having a domain in your integral operator, particularly the boundary integral ones that you have in the Helmholtz case, having a domain that is actually two connected components corresponding to two particles?
Well, I guess it wouldn't be convex anymore.
That is true. Yeah, piecewise convex.
Yeah, we'll have to think of that.
Yeah, okay.
I think it would probably work numerically. We would have more theoretical problems.
Yeah, okay. I think that's probably fair.
Sorry, me again. You assume that it was really smooth, your particle.
Yes.
C infinity, essentially, it's a disk. But what else can you have? I mean, okay, ellipse, disk. I mean, how much can you deform your particle? I mean, I guess you have no corners, but what can you?
No, so numerically, quite a lot.
So what does it mean, quite a lot?
Okay, so well, not more than the exponentials, but for example, that flower that is non-convex and has so it's still quite smooth, but it's not as smooth as a rounded diamond works perfectly.
Would it be anything that you can describe by a Fourier sum, let's say? The sum of...
So the thing is that theoretically we are quite behind the numerics. So for the theory, we need quite restrictive hypotheses, and that's because of the truncation. So the truncation of the infinite series is actually the hardest part of, I think, this expansion. And we've only been able to prove it in 3D for C infinity convex shapes, which is quite narrow.
Which is obviously not C.
It's obviously a lot more restrictive than it should. But that's the best we could do in the time we had. And numerically, we've been pushing and seeing that we can relax a lot of these hypotheses. We haven't really tried anything that's less smooth, or even with corners, we haven't tried at all. It would be interesting to see.
And perhaps it's silly, but is it possible to have a hole inside your object?
We haven't tried at all.
I mean, for instance, assuming some kind of, I don't know if it makes sense. I mean, Neumann and Dirichlet condition on the hole. Perhaps it's not even legitimate. I mean,
so I know that, so in 3D, the group of Ando and everything, they've considered a torus, like a donut. And these would cause problems because they are very high frequencies, or like very high order modes that actually radiate into the far field. So they've shown that for the donut, the mode number 406 actually radiates. And that would be a problem for us because we want to only keep the first couple of terms to make it fast.
Okay.
So
and maybe this was related to something that Brid mentioned. Can you allow for, let's say, multi-layers? You know, so now your particle can have a shell or multi-layers. So how would this translate into your theory? So
for example, different metals.
Yeah, different metals.
Well, I guess different metals wouldn't make much of a difference. We would just have different resonant frequencies. So I think that'd be pretty similar to having two particles, one of each metal. I think that would be, yeah. But we haven't investigated that either.
And mixing dielectric and metal?
We haven't looked at dielectric at all.
Okay, at all. All right. Because I guess that would be super nice to have, you know, a dielectric surrounded by a gold, you know, shell, or I mean, this kind of dielectric gold nanoparticles. Okay, I stop there. It's fascinating.
I was a little curious about how the optimization was done in the last part. I don't know if that's a question for you or Lorenzo. Like, so you've got this, for instance, you've got this functional that you're trying to minimize in order to find. Yeah. I'm curious. So firstly, I mean, how well behaved is this optimization problem? You know, does it what? Firstly, what scheme are you using to find the minimum, and secondly, how well behaved is it? You know, are you stuck in loads of local minima, or? So
we use the functions that were already made in MATLAB. So we just call the
fair enough.
constraint optimization from MATLAB.
Yeah.
It took quite a lot of tweaking because of the dimensions of our parameters. So rescaling everything, and but now it's quite stable. It's pretty fast as well, maybe a few minutes.
And for the pictures you showed us, what value of M? How many modes did you take?
so the same as, nearly the same as what we need in the previous section. So I think around 5 for the flower. But that makes it a lot longer. So the optimization for the flower, the more modes we have, the longer it is, because obviously we are looking for more parameters. And the optimization problem is very good at finding the orientation of the dipole. I think that's pretty easy looking at the scattered field. But then the localization of the Z star is the main difficulty.
Sure. And just to be clear, that's the difference between the cross and the circle, right? Is the
Yes.
yeah,
Yes.
okay. Yeah.
Oh no, sorry. No. The star. So the star is the real position. The circle is the mirage, so what we would see if we were not correcting.
Yeah.
And the cross is the correction. So
yeah, sure. Okay.
the small distance is 11 and the larger distance is 31 here.
Okay, does anybody else have any questions they want to throw at Alice? If not, then I suggest we bring this to the end. Thanks again, Alice. Very informative talk and very thought-provoking. Thanks a lot.
Thank you.